Video. Okay, so today we're getting into the chapter on subnetting and on VLANs and stuff like that. So I thought we'd talk a little bit about subnetting today. I'll have to adjust this to get up on the screen there. Sorry about that. If you can see the screen, I'm going to have to. It's a lot of glare. Let me try this one. That might even be worse. All right, well, anyway, I'll figure it out here in just a second. I might have to turn off that thing there. So we're going to be talking about subnetting, which is one of the things we've discussed it earlier, and so we're kind of taking it in small doses. But so we're going to go over that again. The book also talks about variable length subnet masks, or VLSM. So we'll kind of get into that a little bit, and then also CEDAR addressing. So this is, again, it's not a math class. I do have a short video that I'll post a link to, and we'll watch part of it. And if you feel like the video is useful, you can follow the link and watch it in its entirety, or maybe rewatch it, which might help you out. Sometimes I find that having other people just explain stuff kind of helps out a little bit, because it's one of those concepts that once you get it, it makes sense. But until you kind of get this sort of baseline understanding, subnetting does seem pretty random. It's one of those things that's just kind of like it's a bunch of numbers and math, and it freaks some people out. So I'll try to explain it a little bit myself. I'm going to close the blinds. I'm not sure what's causing all the glare on the screen, because there's like a big spot right there. I'm not sure. Can you guys see the board right there at all, or kind of? I'll move over here more. So I'll maybe use that part of the screen if we can. So move stuff over a little bit. Whoops. And you guys can yell out stuff too if you've got questions or whatever. You can maybe try to adjust the camera some. See if this works here.
That's much better.
Actually a little bit better. It's darker. Can you guys see that better or worse? Worse? You guys can unmute and yell at me. That's
better here for sure.
It's good, Dave.
All right, so I'll try to adjust this. Camera does have some adjustment on it, so there we go. Tone it down. Can't see me, but I don't care about that. You can see the board better, I think, if I tone the camera down. All right, better. Okay, so again, we're going to be talking about subnetting. The classic subnetting is what they call classful addressing. So you have a class A, B, and C. And basically what that means is, I didn't put a bunch of numbers up here, so I'm just going to try to explain it in general terms without confusing you with a bunch of numbers. But basically when they first started setting up IP addressing, you have a 32-bit address. So you have, if you want to think about this as just a chunk of 32 blocks, or 32, and it's actually 32 ones or zeros. And so if you think about having the first part of the address defining how many networks you have, and then the second part of the address defining how many computers or how many addresses are on each address or on each network. And these networks are complete networks. They're not divided up into smaller chunks yet. So in that sense, they're not subnetworks, they're just simply networks. And so the Class A networks you had were huge. I mean, they were giant networks. So, and you didn't have very many of them. So if you think about how many blocks you could fit into this section, you didn't have very many Class A networks, but each Class A network had, you know, literally millions of addresses that were in each network. So what that means is that those individual networks would then have to be chopped up into smaller pieces. So the whole idea of subnetting is that if this part of the address is defining the network address, so, you know, even on your IP address, you can think about the, you know, there's a big number, and then your individual computer has the very tail end of it. So that most of your IP address is defining the network portion of the address. And so if you think about, you know, like a 192.168.254.1.2.3.4, that very last part of the address is what's actually defining the individual, in most of the cases, computers. Oh, there's people waiting in the waiting room. Better get those people in. So again, this is about defining individual nodes on the network, which, you know, you can just think of them as computers because most of the time they're computers, but they could be other things. They could be, you know, routers would have addresses. They could be toasters for, you know, all sorts of stuff can have IP addresses. So the idea here is that if, you know, if you have, well, let's, I mean, draw it like, if you have a whole bunch of addresses over here, and in fact, maybe you have too many. So the idea of networks having too many computers in one group is really where subnetting is coming into play, because the idea is that if you have too many computers on the network, then you're going to have data collisions, right? So things, you know, too many people talking on a conversation at one time is going to cause problems. So the idea is that you're going to take this part of the address and you're going to extend it. So you're going to keep moving this over, and these little chunks here are basically the subnets. And so you're defining additional networks. So if your original network was this big, you're using parts of these addresses to make more networks. So that's how subnetting is working, is that you're borrowing, or they'll refer to it as stealing, bits, or borrowing bits from this part, which means you'll have fewer, and if you want to think about this like, you know, I don't know, dividing up a pizza or whatever analogy you want, that's kind of the one I usually get. So if you have this part of the address that's all for the individual computer addresses, but then you're saying, okay, yeah, we're going to have to create more networks. We're dividing this up, and you can, you know, divide it up into like a block this way, and it's, you know, if your original group of addresses, I'll use black so you can see it better. If it makes more sense to kind of divide it up that way, so you'd have, you know, maybe now you have 4 networks where before you had one big network. So now you have 4 networks, and inside of each network, you lose the top and the bottom address. And this will become apparent in the video when he's talking about a broadcast address at the top. So one of the addresses at the very top of each subnetwork is used to broadcast out to everybody. So it can't be assigned to a single computer. That's probably one of the key elements, is that the, you know, each of these addresses that are included in each block. So you've got a whole bunch of addresses in each block that used to be one big chunk. So a broadcast address is important, and it's not that we lose the address. The address is still there. Think about it that these are addresses that cannot be used on an individual computer because they have a special purpose, right? Okay, so the broadcast, and if I'm at any point, if you have questions, just yell at me, unmute, and just yell. And you guys are so quiet today. It's one of these rainy days too. It's like rainy, and I had to take the dogs out this morning. It's all muddy and stuff, and it's just like, I guess it's a good day to sit inside and talk about subnetting, right? All we need is some cookies and some cocoa and be talking about subnetting here. Okay, so the top address is a broadcast. We lose that address for use on an individual computer. And then the bottom address is basically the address that defines this as a network. So it's the network address for that particular subnet. And then the other address that gets used up but isn't on a computer is typically the first usable address. So this is a usable address, but it's not assigned to a computer. It's assigned to the default gateway. And from your reading, and I know that's very small, but if you're in your reading, the default gateway is almost always your router, right? So you've got these subnets, and the default gateway is one of the addresses. So it's the first usable address in your subnet. And then the rest of the addresses can be applied to computers and to printers and all sorts of stuff, right? So the whole idea is to take a big chunk of addresses, divide it up into smaller chunks, and those smaller chunks can be related. Like these could all be inside of one, look, it could be all inside of one building. If you want to think about it like, each floor of a building could be a subnetwork. And then the default gateways, if the addressing, if you're trying to send information from here to here, the default gateways would be connected in a sense, between the default gateway here and the default gateway here. Ultimately, once something goes out of default gateway, the router would say, hey, is that IP address something else that I'm kind of connected to, or does it go out onto the cloud? The internet is always diagrammed kind of as a cloud because it's just so big and complicated that you can't really diagram it out. So the default gateway kind of makes a choice, and it says, where do I send this to? Do I send this out to other routers that I'm kind of connected to, within my block of subnets, or does it in fact go out to another router out on the internet? But computers in here don't have to make that decision. They basically just look at it and they're saying, okay, if this is an IP address that's inside of this subnetwork, the router does not send it out the gateway. It stays inside of the subnetwork. So that would be like traffic between hosts on the network, print job going to the printer that's on your subnet, stuff like that. So that helps in that sense, is just basically blocking traffic that doesn't need to go out to the rest of the network, or allowing traffic to flow out of the subnetwork and into some other network. But you're dividing stuff up mainly for organizational purposes. Now, one of the things we've talked about so far is that all of the subnetworks that we're creating are supposed to be the same size initially, right? So any of the subnetting exercises we've talked about up until this point, let's say it's a class C network, or whatever it happens to be, if it's class C, then you have 254 addresses to start with, right? And this is, class A, class B, class C. This is in your book. We've kind of, hinted at this stuff up to this point. We've been working with it a little bit. I told you it was going to come back to haunt us. So if you have 254 to start with, you could divide this up into 4 equal parts, right? And what's 254 divided by 4? We've got our calculators out there, roughly.
61.
Or you can guesstimate. You guys are so quiet here. Help me out.
It's like 63 and a half.
All right. And you're trying to get you guys to play along a little bit.
63 and a half.
The first person that answers the question gets 10,000 brownie points.
63 and a half.
Can you hear us, Dave?
Dave.
Nobody? Come
63
on,
and a half.
Things. There you go. Come on. I see some people unmuting.
63 and a half.
Or is
63 and a half. Oh my.
Jason's just laughing.
Yeah, he's laughing at me.
Okay. If you guys aren't playing along, then we can all just go home today. So.
Hold up, maybe this will get his attention.
Okay, so we're gonna pretend we're gonna do Elliot's going like this.
60,
You guys can't hear me?
63 and a half. Yeah, he can't hear it.
Oh, sorry. I'm muted. There, I need to take a look at the chat window.
Can you hear us?
Yeah.
63 and a half.
Okay. So you guys have been able to hear me, right? You can hear
Yeah.
me, but I couldn't hear you. Okay. I'm so
Yes.
sorry. Yeah, I had the TV set that functions as my speakers as I'm wearing headphones is muted. So technical difficulties. That's pretty funny actually. So sorry, somebody holding up signs or something. And all
I was
right.
about to write it on a piece of paper and put it at the camera.
All right. Sorry about that. Yeah, I had the TV muted because I was watching this YouTube video and it was real loud, so I muted it. So it was a YouTube on subnetting of all things. All right, so roughly 63 addresses. Thank you for playing along with us. You could do that in our head. So, and so if you're forming equal parts there, now I'm all thrown off. If you're forming equal parts, that makes sense. So let's say, we'll just round it off. We'll say we've got 60 addresses in each one. And, you know, that works if you have 60 hosts pretty much on each floor of the building. So like, let's say we're trying to divide this up and you've got routers, or they can be layer 3 switches as well. So if it's a switch that's functioning, that'll do layer 3 stuff. It's where you can create VLANs as well. So in the book where it talks about VLANs, a switch can do some of the functions of a router if it's a special kind of switch, right? You know, hubs are layer 1, switches are normally layer 2, going back to our good old OSI model. Routers are, since they're dealing with IP addressing, are layer 3 devices. But you don't always need a router specifically, especially if you have to have more ports. So if you're combining the features of a switch, which typically has a whole bunch of ports on it, now your home routers are a little bit of an anomaly. Your home router is actually multi-function device, right? Your home router does firewall stuff. It has some switch ports on the back of it, usually like 4 or 6. And it does wireless, right? And it's also functioning as a firewall. I'm still laughing about me having the TV muted and thinking, God, these guys are just not even playing. I'm asking them a simple question and they can't even answer that. I mean, I'm just going to go home today, getting all frustrated. So that is very, I mean, it's funny. I think it's funny. Keep myself entertained. All right. So at any rate, let's say you've got, well, we're going to pretend like we've got people working in the building, right? And say we've got 30 people on this floor, 40 people on this floor, 70 people on this floor, and maybe 20 up here, right? So now the idea is that if we made 4 equal subnets, then it doesn't really match up very well with the number of people that we have on each floor of the building. So then that's when the idea of variable length subnet masks come in. And why do we care about this? Well, it's kind of important if you were into, if you get into more of the hardware part of the network side of it, network engineering, you'd be setting stuff like this up. Now, the other side of this, that's kind of the flip side of this, is that you typically would not be doing a Class C address in a building, a large network, right? And the reason for that is that the Class C networks, this is where you've got like the 192.168.5.20 or whatever it is. Most of the Class C network address is used for this portion, right? For defining the networks. So you have, many, many, many Class C networks, and each Class C network has a fairly small number of addresses for the host portion, for the computers, right? Well, the other reason you see this is the 192, what's special about 192 addresses? Now I can hear you guys in case you're yelling at me. Public, private, what's unique about a 192 address from our experience?
Isn't that private?
Yeah, I'm not sure who said that, but excellent. It's private. And when something's a private address, what does that imply?
The information is not publicly available.
Right. And in this case, the public is the internet. Okay, so on a private address, you would have private addressing behind the firewall, and then your router is doing NAT, right? The network address translation. So your router, you know, in your case, you got this home router, you've got a public address that faces out towards the internet. And so if you guys at home type into Google, what's my IP, it'll tell you what your public address is. So your public address is an address that's routable. It's available out to the internet, and the other devices that are on the internet can talk to it. You know, it's a public address. Behind the firewall, that looks like rabbit ears there. This is supposed to be a router. Behind the firewall, you have private addressing. And home routers, we use the 192.168 blah, blah, blah number. Because, you know, home router, you're not going to have more than 10, 15, 20 devices on a home network typically. You know, maybe you have more, but you have 254 addresses that you can use on a home network. And they're not subnetted. It's just one big chunk of addresses behind your personal home router / firewall. But they're private addresses, which means that the 192 address can be the same address on my router as it is on your router. You know, anybody in the world can use 192 addresses behind the firewall because the firewall is doing that translation for them. In larger corporate networks, you would use a 10 dot address. So a 10 dot address, the first part is defining the network, and then you have this other big chunk, right? You have this other big chunk for all the hosts on the network. So I guess the moral of the story is when we start talking about variable length subnet masks in your book, if you're reading about VLSM, it is kind of an interesting concept, but then you start thinking, okay, well, if I was using a 10 dot address, I could make these addresses, instead of having 4 subnets, I could have 1,000 subnets if I wanted to. You know, if you plug it in, if you guys plug in or Google search for a subnet calculator, you can type in some numbers on the subnet calculator. And so you type in the IP address or the network address, and then you can start playing around with different subnet masks. And the subnet mask, as you start moving it this way, right? You start, so the default subnet mask for class A would be 255.0.0.0. So each of these chunks between the dots represents 8 bits, right? So 2 to the 8th power versus 1, 2, 3. That's 2 to the 24th power. And I'm not going to try to calculate. I'd ask you guys for help on that, but we already had that fun to begin with. So 2 to the 24th power, that's a lot of addresses for each network, which means that you can create a whole bunch of subnets. You know, you could move this over to the right. So this subnet mask, you can think about it like a sliding scale. I'm going to make it red. So I can move this all the way over to here, which means I have borrowed 8 bits, or 2 to the 8th, and that leaves me with 16 bits left over for the host computers. So if somebody does have their calculator, you can do 2 to the 16th, and you get something like 64,000 addresses, right? So if I've created a bunch of subnets, I could have 64,000 addresses on each subnet to play with, which means that, you know, in our original thing, I had 60 here, 60 here, 60 here, 60 here, you know, 30 people, 40, you know, you could see, and then this one was over by 10, right? Well, instead of having, you know, subnets with 60 addresses, I could have subnets with, you know, 10,000 addresses if I wanted to. And then it doesn't matter if I have 60 here or 70 here or 80 here or 1,000 here, right? Because so VLSM is an interesting concept, but if you're doing stuff behind the firewall, which most of us will be, we won't be dividing up addresses that are public addresses typically. right? This was more of an issue with public addressing, but right now all of the IP version 4 addresses are used up. IP version 6 uses a whole different system. It doesn't use traditional subnet masks. IP version 6 uses a whole different system. We're going to continue to see class A, B, C addresses, you know, the 32-bit addresses. So we have IP version 4, IP version 4, and IP version 6. So if you go into your network settings on your computer, you can see you've got IP version 4 and IP version 6 addresses. You're going to continue to see IP version 4 used behind the firewall, right? And then on the front side of the network, you know, you might see IP version 6 on your router interface, stuff like that. Okay, so yeah, I'm getting myself sidetracked and I've got a huge mess on the board at this point. But the main thing to keep in mind is that your subnet mask, as it's moving to the right, creates more networks. But as you move it to the right, that means you have fewer numbers left over for your host computers. But if you're using a class A address or class B even, you still have lots and lots of numbers to assign to computers, even if you create quite a few subnetworks on your network to begin with. Now the math that's involved, there's a couple of good websites. I've got a video queued up that we can watch. I can share with you a little bit to watch how other people try to explain the idea of subnet masks. And then the other thing that they talk about is CEDAR addressing, which I'll explain just briefly. So let's say on this original class A, it was a /8. So if you had the first 8 bits for your subnet mask, that would be a /8 network. Class B would be a /16 because it's this first 2 octets. Octet meaning 8 bits. So you've got 8 bits plus 8 bits. And a class C network. Now again, these are before you create subnets. You have a class A, class B, class C networks that have not been chopped up yet into smaller pieces. Here's a /24, since it's got 8 bits plus 8 bits plus 8 bits, right? Which means you have 8 bits for your host section, or 2 to the 8th, right? 2 to the 8th is 256, but you lose your top and the bottom address, which means you have 254. So 2 to the 8th minus 2 equals 254 addresses on a class C network before you chop it up into pieces. I hope that helps a little bit. Now, once you start chopping it up into pieces, this number is not going to be /24 anymore, right? just humor me. Some people, yeah. So everybody else is like laughing or okay, yeah, thumbs up. All right. So as this moves to the right, as we start creating additional networks, where'd my red pen go? Lost it. Here it is. So as we start creating additional networks, you know, the host portion shrinks, but this number is going to change. You might get a /26. You might get a /27. Something like that. Now, the variable length subnet mask idea is that if you have different subnetworks, some of them could be /26, some could be /27, that the idea is that with those different networks, each one could have a different subnet mask. Whereas with traditional subnetting, all of the networks that you're chopping up would have the same subnet mask. Does that make sense? So variable length subnet masking, VLSM, is kind of a discussion that they have in the book as well. So that's kind of the idea, is that if you can make some of them this size, so you'd have some subnets that were smaller, some that were larger, in order to accommodate different sized networks as you were working this out. Okay, so class B networks, you know, this can be slid all the way over here too. So I mean, with class B, don't associate, so this is the standard subnet mask before you chop it up. But a class B network could have something that looks like a /24. So like even in our classroom here, our class B networks were chopped up. And so our subnet mask is 255.255.255.128. So we've actually moved it clear over here. So we've got /24. Ours is a /25 since we've got all of this plus one more bit that's been borrowed. So we actually have a /25 address. And ours is a class B. And how do I know that it's class B? Well, in the book, it talks about that too. You look at the first part of the IP address. So the class A's are like from, 1 to, what is it, 126, something like that. These are like 127 is a special number. So these are like 128 up to 191. These are like 191 up to what is it? I can't remember off the top of my head, the higher ones. And then you do have a class D and a class E that aren't used for anything that people use them for, right? They're reserved addresses. One of them's for multitasking, or not multicasting, excuse me. And then, maybe there's some special IP addresses they're using at like Area 51 or something, I don't know. So class D and class E do exist, but you're not using them on networks or computer systems. Okay, so I'm going to show you the quick, share my screen here with you. We've got a quick little article that we can look at. I've shown you this before, but he does a pretty good job of explaining subnet masking. So now I'll turn the camera up a little bit. Yeah, that's weird. The camera, it just blows out the screen if I raise it up too high. So I can be either dark and you can see the screen. At least this camera came with software to adjust it. A lot of them don't. And this was a pretty cheap camera, but okay. So I'm still laughing about having the TV muted so you guys couldn't hear me. I think I can hear you now. So I've got it turned up all the way. All right. Okay, so we're going to look at good old Punky's how-to page. This is, I will post this in the chat room, but also on the discussion board as well. I'm looking at, everybody's like, look at chat, look at, Jason's like, look at chat, we are 63. Okay. Yeah, the chat room's funny. And I couldn't see the chat from clear over there, so I was like, I don't always have it up on the screen. I've got two monitors, but even so. Oh, well, it's the joys of online learning, so. All right. Okay, so I'm going to share my screen real quick, and we'll look at this guy's web page. He does a pretty good job of explaining this. I've used this site in the past. It's funny, for class, I've actually it's real basic HTML too. This guy's website has been around forever, but he changed it a few years ago and threw in a few F-bombs, I think, just for fun. So I edited his web page and then stole it, plagiarized it, and put it on my own little website in the classroom. So if it was local, I could just share the plagiarized version that I've edited. Okay, but the first part, so he goes through the steps. He talks a little bit about a couple of different things, like what a default gateway is, which is good explanation about what an IP address is. Static versus dynamic addressing. Most of the time in a work environment, your computers that you're going to be working with at work are going to be given addresses dynamically by some sort of a server. At home, your multifunction device, your router, is also a DHCP server. So when you think about it, those little routers we have all running at home are really pretty amazing devices that they do so many different things at one time. So they function as wireless, they're a switch, they do the gateway router stuff. Yeah, pretty cool. But static addressing, what you might find, especially next quarter when we start looking at installing server into, let's say, a Hyper-V environment, is that certain things that a server does, it wants to have a static address, meaning static that it doesn't change. So that's when you'd have to go into your network settings and you'd have to apply the number yourself as an administrator. And when we do this at home, what you usually do is you let the computer get an address first. So even if it's in Hyper-V, you let it get an address. You go into ipconfig and you see what the address is, write it down, and then you apply it statically, so that you know that the address will function with your router and the rest of the subnetwork, right? So you have to have an address that makes sense to the other computers. But normally, addressing on most computers in a network, so most devices are going to have dynamic addressing. Okay, so once you figure out what your address is, and you can do this using ipconfig, you open up ipconfig and you see what your address is. So I'll have your ipconfig. Here's mine. So my address in the classroom, and here's a difference too, is that in the classroom, they gave us public addresses. So we just talked about public versus private. And if you notice, if you look at my address, it's 134.39.158.14, and it's also static. So the classroom, a few of you had been in the classroom before, we have to set the computers up. You assign the addresses. They're actually written on the desk. So if you look at the first octet of 134, you can see that that actually fits into a class B network range, right? So the first step in trying to figure out anything to do with subnetting is to look at your address and figure out what's your starting point, what's ground zero. Well, my starting point for our network to try to backtrack and figure it out is that it was in fact class B. And then you look at the standard subnet mask, that's your starting point for your subnet mask, and you look at the difference and you're thinking, okay, your standard subnet mask is 255.255. Our address is 255.255.255.128. And you're thinking, okay, well, if it used to have 16 zeros in a row, so if it's 255, that represents 8 ones, right? Another 255, that's 8 more ones. So there's 16 ones in a row. And if you think about the subnet mask kind of being like a sliding window or masking tape that's kind of sliding over and covering up the network portion of the address, then you can see that ours has been modified by another 8 bits plus 1 more bit. So if you can, if you can still see this up here, 128, 64, 32, 16. This is our little cheat sheet for 8 bits worth of binary. And so 128 is one more bit added on. So we have a total of 8 plus 8 plus 8 gives us 24, plus 1 more bit. Our network subnet mask would be a /25 address. If you were looking at CIDR addressing, and that's a CIDR. That's in the book. So this is in your chapter that's on subnets and VLANs and all that kind of good stuff. And the reality is that again on the back side of a firewall, you can create many subnetworks, and you're using private addressing. So the idea of having to really determine the size of the subnet and how many subnets you're going to end up with kind of goes out the window if you use a class A network. And so like if I run ipconfig on my office computer that's on the rest of the campus network, its address is going to be like 10.17. something, it's a 10 dot address. So it's still private, but it's class A. And I hope at this point you're starting to see the distinction that if it was a class A network that's divided up, not only is it private, but it had, millions, thousands of addresses that can be chopped up into subnetworks, and you don't really have to worry about running out of addresses, right? As opposed to the example that Punky is doing here. This is Punky's how-to pages. At one point I went up to his the URL and I took out the how-to subnetting and stuff and looked at his main. So he has also, I believe, how to host like a Star Trek convention, or he used to. So this guy is like an uber nerd. He is like the king of the nerds that host. And his website's been around forever. And I know lots of other places use this kind of as a good little primer on subnetting. And I think he thinks it's funny that he threw in some swear words just to throw people off. And he's like, okay, if you don't like it, don't use my website, I guess. I don't know, it's kind of funny. Okay, so the little formula that he's got, the 2 to the nth minus 2, that's kind of related to what I was talking about here. So if I had 8 bits originally, 2 to the 8th is 256, minus 2, that's that top address and that bottom address that can't be used for host computers. So in this case, the same formula is used, but we're dealing with dividing it up into smaller chunks. That was figuring out how many addresses we had for one big I should point towards one big subnet that was a class C, right? So he's thinking, okay, so we have, originally we have 256 addresses. They want to, if we walk through his formula, so he says they want to have 20, so he says if you need 25 subnets. So here's the deal, you know, if you think in your head, again, we go back to our calculators, which was kind of funny earlier. If we have 256 addresses and we want to divide it up into 25 pieces, that's not going to leave very many addresses for each network, right? I hope you guys are following along and you're like, sure, just nod, like humor me, sure. All right, so so right away we can see with this example that they're making up something and it's not going to be very practical, but it's just doing it to kind of figure out what's going on, right? So here he's got a 192 address. This is a class C address range. Here's the default subnet mask. And it's saying, okay, so how many, we have 8 bits to start with hanging off the tail end, right? 255, 255, 255, that's the network portion. We've only got 8 bits left over to play with. So at this point, he says 2 to the nth. So if we have a little cheat sheet, he's got it here on his board here. Here's this little cheat sheet. I usually draw this up on the board here, but this is a good little cheat sheet. So 2 to the nth power, in this case, the n represents how many bits we want to borrow. 2 to the 4th is 16. Now that's not enough, right? Because we wanted 25 subnetworks, but remember it's 25, it'll be 2 to the nth minus 2, because you're losing those top and the bottom networks. So in this case, well, I forgot to mention that too. When you're subnetting, not only do you lose addresses out of each subnetwork, you lose the very top and the very bottom subnetwork as well. So there's a lot of wastage involved. And if they're addresses that you're not paying for, like if they're private addresses behind the firewall, you don't care that you're losing addresses, right? But think about this originally when they set this up, that these were public addresses that were given to businesses. And so all these class A networks were given out to businesses like IBM, HP, you know, all these big companies back in the day. They got these gigantic chunks of addresses, but they couldn't use them all in one network. So you have to subnet them, right? I mean, you just can't physically have a network with millions of computers on it. So you had to subnet them, but you're losing, you know, tons of addresses when you do that. So the analogy I usually use, if you have a giant pizza and you chop it up with a real thin blade, you don't lose much. But subnetting is messy. It's like you're chopping up the pizza with a 2x4 and you lose big chunks of your pizza, which is sad. Okay, so back to our little formula here. 2 to the 4th isn't big enough. So you have to move to 2 to the 5th, which is 32. And then minus 2 will give you 30 subnetworks, right? So that's what this little thing walks you through, is that he's actually going to create 32 networks. You're going to lose the top and the bottom one. So you end up with 30 subnetworks. And then he walks through the rest of this. So that says, okay, so there's our subnet mask is 128 plus 64 plus 32 plus 16 plus 8. That's the 5 bits that are stolen. So that's adding up this number plus this number plus this number plus this number plus this number. So you start from the left-hand side, if you can still see on the screen, and you're adding up these. So if you think about it kind of like they're like a calculator where the numbers are dropping down, a 1 means that the switch is turned on, and a 0 means the switch is turned off. So in this case, you're taking your original subnet mask for the class C. 8 bits plus 8 bits plus 8 bits is /24. And then we're adding 5 more bits. 1, 2, 3, 4, 5. So we're extending it this way, right? So it's going to be, our last one is going to be a /24, or excuse me, not a /2, it's going to be a 248. So here he's got the first 3 octets aren't changed. That's as big as they can get, 255. And then the last octet becomes a 248. And that's 128 plus 64 plus 32 plus 16 plus 8. If you can see where my mouse is turning it blue. Okay, so that's how he comes up with the 248. If you were adding that up, you'd have 24, 25, 26, 27, 28, 29. We'd have a /29 address for subnet mask if you were doing the CEDAR addressing, right? The first 24 bits plus 5 more gives you a /29 address or subnet mask address. Now, you're never probably going to see one of these in real life because, as he explains, as we keep going on, he's like, okay, you use the same formula for the number of hosts per subnetwork, but instead of using the 2 to the 4th, you're using the how many bits you have left over. So this part gets confusing because the formula is the same, but you're changing what the n represents. So in some sense, it might be better to say 2 to the x power minus 2, and then 2 to the y minus 2 for the other portion. But they use the same formula, so some people get confused because the n changes value. And I know this is sounding like math, and some people are like going, oh no, this sounds like math to me. But the math that's involved is fairly straightforward. If I can do it, you guys can do it, because I'm not a math major. All right, so if we have 3 bits left over, we've stolen 5, which means we have 3 bits left over. So that's where this part of the formula comes in. And then I will post this on the announcements or discussion page for the class. So if you guys want to take another look at this and kind of walk through it yourselves, it sometimes helps to take your time and walk through it. We're running out of time too, and so I'll post a link to this video. I'll put it into the chat right now, but I will also try to post it into the discussion area for our class. Okay, here we go. All right. Okay. Oh, I should have done. All right. So there's 2 things that are posted there. Sorry, that was. Separate them out there. Okay, so that's the post for the YouTube channel, and there's a ton of those out there too. So one of my students found another video. I couldn't find the exact same one that was in the other class this was spring quarter. So here's the one for Punky's how-to pages. I'll separate this out again. All right. So those are the 2 that we've been looking at, and the video we didn't have a chance to look at yet. You might explore a couple others if this is just starting to gel and make sense to you. Hopefully it's starting to make a little bit more sense. The concept for variable length is interesting. I don't know as a network person if this is, if you're looking at this and thinking, this is crazy, what am I going to do with this? For the most part, behind firewalls, you're using private addressing. So you can kind of go crazy and use, a class A address. You can have subnetworks that have thousands of addresses available. It doesn't mean you're going to use them all. You just have, giant subnetworks, and you might use 50 addresses out of an available 1,000 or so. It doesn't going to cause a problem because you have so many addresses to choose from to begin with to chop it up into pieces. Okay, so in the example here, he does 2 to the 3rd power minus 2. So that's 8. You lose the 2 addresses, so that's only 6 computers per. That's only 6 computers per subnetwork is what happens in this example. And it says, yeah, but you're the bozo that wanted 25 subnetworks to begin with, right? So in this example, it's purely academic. You're not actually going to use this type of subnet mask in a class C private addressing scheme because you'd end up with 25 networks with 6 computers or printers or whatever they are in each network, and that's really not very functional, right? So then he goes on to try to explain the first usable address and the last usable address from each subnetwork. Keep in mind that he's not showing the top and the bottom subnetworks. So if you're thinking, why is he starting at .8? Well, the very, very bottom subnetwork would be .0 to .7, and that one's not used at all, and neither is the very top subnetwork. So it's very wasteful. You lose addressing, but if you're starting with 65,000 addresses in a class B, no big deal. Those are the 172 addresses that are private. 192 addresses for a home network work fine. Big corporate networks might use a 10 dot addressing scheme, 10.00. So you literally have, millions of addresses that are available. All right. I'm hoping this made a little bit of sense. Helps you with some of your reading in the chapter on subnetting. The CIDR addressing, CIDR, is the idea of using a /24 or /28 to represent, instead of having, you know, 255.255.255.128 or whatever it happens to be. It's easier to write out, and you'll see this in routing. Routers will have that configuration menu. Oh, we're way over time. All right, you guys. Some of you will be back for the 10 o'clock hour. So if that's the case, we'll see you in just a couple minutes, and we'll take a break and let our brains relax from all the subnetting stuff. And we'll see you guys in a few minutes. All right.